Hi, this is Prasad Gore from Electrical Science Solutions. Recently, utility company has changed its tariff related to power factor. So this video is an attempt to clear confusions regarding power, energy, power factor, and utility tariff. What is power factor? What is energy? What is power? So what we know, power is kW and energy is kWh. Let's understand this. We all are basically interested in knowing energy. Basically generating stations, what they are doing, they are just converting one form of energy into electrical energy. So basically the energy is the main part that we are going to look into. Then what is the significance of power? By definition, power is the rate at which the energy is transferred. So the rate at which the energy is transferred, so power is energy divided by time. So it's simple. Let's say we consume 3000 units of electricity energy, that is 3000 kWh. So we can have 3 hours with a different power drawn at every hour. So let's say for first hour 500, 5500 into 1 hour, it's 500. In second hour, the rate, the kW is 1000, so it is 1000. Third, it is 1500, then it is 1500. So total energy is 3000 in 3 hours. So what is the average power? The average power is 1000. So 1000 into 3, that is 3000. The similarly, if I have the average power of 1000 and if I am consuming the power at the same rate every hour, still I'm getting the energy of 3000 units. So there is a two different scenario. At 1000 constant, here a different power at different hour. So what we are interested, or the basically the generating station will be interested to knowing what is the total energy consumed and at what rate it is required to be delivered. So that is why the energy, that is why the generating station can accommodate this kind of power requirements in their generating stations. Okay, so as I said, the instantaneous power and the average power. Instantaneous power is of basically of not interest, but the average power over certain period is of interest, and the maximum power of certain at certain interval, that is important. So let's understand how measurements are done in meters. So let's understand this. What is power? Power means is basically the voltage into current. Simple formula. Uh, Voltage into current. So here, what I'll say, here we have collected some data, uh, some data of, every 78 microseconds we have one voltage value, one current value, and this way we have just plotted this waveform. This is basically current. This is voltage. So what we have taken here, the IRMS of 532 ampere and voltage is 243 ampere. With the peak is 755, voltage peak is 345. Presently the angle is 0, that is power factor is unity. So as said earlier, power is of instantaneous power is of no use. These all are VI and II is instantaneous voltage, instantaneous current, and PI is nothing but, if you can say, we are just multiplied this V instantaneous into I instantaneous, and that is P instantaneous. So P instantaneous on every 78 microseconds. This is reactive power instantaneous. What measurement meters they do? They just shift voltage signals by 90 degree and they multiply this V instantaneous into I instantaneous to get the I instantaneous, reactive power instantaneous. That is this reactive power and this is active power. So this is another graph. For different things we have made, basically the it is averaged over a complete half cycle, but we have this is the average over complete cycle. So this is basically the Basically basic power factor power that is shown on any meter. So let's understand this first. Energy is nothing but the integration over period t pi dt. So p instantaneous into time. So we know that power average is E total, the energy consumed total over a period of time. So E by T. Substitute this, if P average is nothing but 1 upon T, 0 to T, Pi dt. So this is energy and this is 1 upon time and this is the average power. So if we have this kind of equation or this kind of integral, then this function is nothing but the average value of this function. Pi is the function, and if you take the average power, average of this, we will get the power. We are talking or saying this is the average power, but simple understanding. You have to go a little deeper onto this, but just understand that if we take the average of any period, you will get the complete average power of that particular waveform. Okay, let's forget this. So like wise we have made measurements on this complete over one cycle. So this voltage, this is current, and this is complete wave cycle. So okay, another things that I'll just do some maths for you. Okay, now we'll go. This is understood. Now we'll go to this interesting facts. So you have you can see here the current I is lagging by 90 degree. So 90-degree lagging means definitely this is an inductor, a perfect inductor. We have a current value, voltage value here, current value here. You can see the peak of the voltage comes first and then current. So current is lagging by 90 degree, 0.055 millisecond and 10 millisecond. Here you can see this is power, the power consumed by the inductor. In the first 5 millisecond, the power is delivered. Let's say in this 5 millisecond, the power is consumed, and in the next 5 millisecond, it is delivered. So over average, the power comes to be zero. So this is basically zero, but due to some the averaging, it is coming one, but it is actually zero. So this is zero because each halves are zero. But here you can see the kVR value is 64. The reactive power is 64. But the first 5 millisecond minus 42. These are the kW. So 42 kW. Actually, the generating station has to deliver 42 kilowatt for energy storage in this inductor. So energy stored in this particular half cycle, not half cycle, the quarter of the cycle, the 5 millisecond. So energy is stored, then energy is released. Energy is stored and energy is released. So net energy is zero. The energy has to be generated and delivered for this inductor in this first 5 milliseconds. So what happens? The generating station fuel consumption occurs in this particular region. But in the next region, that utilized energy is given back to the generating station. So the 42 kilowatt is the actual power that is absorbed in first 5 millisecond. Minus 42 is given back in next 5 millisecond. So if you can see, this is average in average power in first 5 milliseconds. So we have just taken first 5 millisecond wala average of this pi, and in second 5 millisecond we have taken this. So this entire cycle is divided into 5 millisecond, 10 millisecond, 15 millisecond, and 20 millisecond. Okay, 42 and 66, just understand this. So this is 64 and 66, this is a reactive power in kVR, but this is actual consumption is 42 kilowatt. 42 kilowatt consume, 42 kilowatt delivered back. Okay, now let's understand this. We'll go here. RMS value 533 ampere for 243 voltage. Here I have the power factor, perfect power factor of 1, then you can see my average over complete cycle is 129, 10 millisecond, half cycle or complete cycle, it's one and the same. Complete cycle is 129. My apparent power, which is basically the kilowatt divided by the power factor, is also 129. So if I am utilizing a generating station's power at power factor 1, the maximum power that I can get is 129. Just let's understand this. And first average in first 5 milliseconds is 129, second 5 milliseconds is 129, 129, 128. Actually, it's 129. But if the average over complete cycle is also 129 and average over of every 5 milliseconds is also 129. So B5 minus F5, that is actual power and apparent power. The difference is zero. Okay. Now what I am doing is I'm just making the real world readings. Let's say 30-degree angle, that is power factor at 0.866 lagging. Here you can see the average power consumption is gone down to 112. Earlier it was 129, equal to the apparent power, but now it's 112. So you are not utilizing your complete power available for this current. You are just utilizing average power of 112. Then where does this extra power of 17 kilowatt uh, goes? You can definitely see here you are having the 66 is your kVR is your reactive power, 112 is your active power. But now you can see all this average of 5 millisecond. In first 5 milliseconds, it's 70, it's 153, 153, 69. Why this is unequal or uneven scenario at every 5 milliseconds? So as explained in this inductor sheet, 66 was what we understood here, the 66 kVR, the energy was 42, 42. So here also, if you can see, in this particular region, 153 kilowatt was the average required. Your average power is 112, but in this particular quarter of the cycle, you wanted 153 kilowatt power from generating station. So 153 means your actual requirement. So out of 153, 41 kW was utilized to charge your inductor. And if you minus this 153 minus 41, you will get 112. So this is basically 153 minus 112, it is 40, 41. So your average power requirement of this region was 112, but you were inductive load, you wanted 41 kilowatt extra for charging your inductor. But the next cycle you are requiring 112, but it is 69 because 41 is given back in this next cycle. So if you take the average, it is 112, but if you take the maximum, it is 153. So 41 was required. So the generating station has to consume their fuel for 153 kilowatt. Understand this. Though they will charge you for 112 because the average power used by you is 112. But in particular, these quarters of cycle, you are requiring extra 41 kilowatt. So let's understand this. Will lead to you a very good figure of 7% incentives. Now we'll just try to give the explanation. So the next explanation may be the answer for this why the 7% incentives. Let's understand this. You maintain a power factor at 18.2, let's say 950 or 28 point, oh sorry, 25.8, 25.8, 25.8. Okay, 90 is a power factor. So let's understand this. 35 kilowatt, 116 your power, 57 you're lagging, 10%. 10% loss in the power. If you maintain a power factor of 1, 10% loss. So at power factor 90, if you see, you are not underutilizing your power, underutilizing the generation station by 10%. So if it is considered that the plus or minus 10% underutilization or overutilization is allowed by utility, then at 0.90 you are not charged or not given any incentives. Okay, but if you see this 7%, what does this indicate? It indicates that at this particular region, you are asking 17% extra than what they can give you. So again, out of this 17 extra that you require for charging your inductor or inductive load, 10% if allowed as a over utilization, still 7% you can save from utility. So if you maintain a power factor from 90 to 1, they can actually give you 7% incentives on the kWh utilize. So if this is power factor is 1, you're utilizing 100% of it, then there is no power factor penalty, or they are saying you are utilizing at your best. But if it is 25.8, that is 90 power factor, you are underutilizing it by 10%, overutilizing by 17% here. So on an average, 7% you are still overutilizing it, underutilizing it, because 17 is overutilized here, and on an average you are underutilizing 10%. So they don't want to charge you anything, any penalties here, because 10 plus or minus 10% is allowed. So here if you, on an average you are still in the region of limit of 10%, but on this quarter cycle you are 17%, means 7% extra. So they are just saying that, you maintain a power factor of your unity and you will give we will give you 7% incentives. So that is basically maybe the reason that they are offering 7% incentives. Now then, why after 0.95, if you maintain a power factor 9.1, they don't offer you any incentive still. Let's understand the reason. Let's say 22, you are maintaining 9.2. So what happens? You are underutilizing by 7%. Here you are overutilizing by 6%. So you are released 3%, but still you are utilizing extra 6% here. So they just don't want to give you any incentives at this. But let's say 18.2, that is 950. 950 means what? You are underutilizing by 5%, okay, and you are overutilizing by 5%. So at this junction of power factor, you are exactly underutilizing and overutilizing as matching. So the it is exact 10%. So after 9.5, they can give you that 7% incentives. Okay, this is the basic of why there is a incentives and why there is utilization. So and why there is a though you have 123 here, 148 here. So this is lagging. Again, in the leading, it is the same scenario. If you see, let's say minus 30, that is leading power factor. So in leading power factor, the apparent reactive power is minus 66, that is capacitive reactive power. Here also same, you are not utilizing your energy at 100%, still you are under utilizing by 13%, and same still, but only the region has changed. 153 here, 153 here. As I said, the region has changed here. It was earlier it was different waveform, and now it is different waveform. It's a capacity, it's just capacity, but everything remains same. Though it is capacitive or reactive, it doesn't matter, but you are underutilizing it or you overutilizing it for a quarter of the cycle. So this is basic things. For more deeper understanding, you can contact me at any point in time to get the knowledge out of this. Now we'll just move to how does your bill looks like. Okay, let's understand this. This is your consumption, the average consumption for 12 hours, and this is average consumption for rest of the 12 hours. So what happens? You are maintaining the power factor at, let's say, 200 kilowatt is your average consumption for 12 hours, calculated to 2400. That is 200 into 12. That is 2400 units for this 12. 20 kVAR is your average inductive power requirement. So you are in this 12 hour you are maintaining power factor of 995. So kVARHL is 240 again because it's 20 and this 12. So 200, 2400 and 240. So your power factor is getting to be 995. Your RKVSC that is leading is 0. But what happens after the load is reduced? Maybe some of your equipment has a capacitive load. So let's say at this particular rest of the 12 hours at low load time, or maybe the time where the APFC panel is going leading by some, let's say 18 kVAR, and at this particular time the power factor is 9.2 maintained, but 9.2 leading. So KVRSC will get calculated here on. So KWS consumption to 528 because of low loading, and KVRSC is 216. So here you can understand the power factor is 926 in this particular region. So in 12 hours it is 995. You maintain it 995. No capacitive consumption. Rest of 12 hours you maintained it at 926, but 18 as a capacitive. So the consumption of KVRSC is 216. KVRHL 240, KVRSC 216. Those get added now, will get add now, and the KVRH consumption will be displayed as 456, and KWH is 292928. That is 2400 plus this 528 2928, and the average power factor is 0.988. So earlier what was happening, this 18 kVAR was not at all calculated, so make it 0. And if you can see this, the KVRSC was not at all calculated. The KVRH is 240, this is 997. Now they are starting KVRHC as well. So this goes to 456, averaging your PF down to 988. So 995 earlier, 988 now. So this is simple. The weekday that you have uh, 5 into this is the average total per day. So 2928 consumption per day kWh for 5 days, kVRH for these 5 days, working 5 days. 2 weekend, what happens the weekend, this load remains 24 by 7. So you just multiply this by 2, and actually I have to do it by 24 hours, but still okay, 216. So average power factor will come down to 985. 985. So though you have a APFC panel, and if you are having this kind of scenario, your power factor will not be maintained at 995 or 99, above 99. So it can be worse than this. It can be better than this. If you have just two, okay, you just have -2, or you can have just -5 kVAR as the average. You are having 995, wherein you will get 3.5%. Okay, now another point to miss, I just missed that earlier it was, I'll just 18.2 it was, no, it was 25.8, that is 90. 7% was given, but now they are reduced to 3.5 because maybe now, as I said, they have started KVRSC also. So for this 995, they are just made it half because the contribution for KVRHL and C will be equal. That is maybe the concept behind getting to 3.5% now. And this will again, what we understand is that basically KVRH calculation of KVRHC and KVRHL is nothing but the calculation of KVAH consumption. KVAH consumption. So sooner or later the KVH billing will come, but still in KVH billing there is some challenges in calculating the KVH in different with the different methods, and this lead to a different readings. So I think the KVH billing may soon come. Okay, that's all. The disclaimer is important. Don't use this information for anything else. just a knowledge purpose. Hope this video is long, but still you will find your most of the confusions cleared. Thank you very much. You can always contact me at prasad@electricalscienceSolutions.com, and this is my mobile number. You can call any point in time. Thank you very much.